Common charges on monatomic ions is a topic usually mentioned in the first few weeks of general chemistry when students learn about the periodic table and naming elements and compounds. But it is never really explained until later in the semester when electron configurations are discussed. Let's try to tie the two here. Monatomic ions are single atoms that have gained or lost an electron, or electrons. For example, neutral sodium has 11 protons and 11 electrons. Protons are positively charged while electrons are negatively charged. The net charge is 0. But sodium tends to lose one electron and becomes sodium ion, or Na+. Here, the net charge is +1. We'll talk about why this is in a moment. But first, let's define the types of ions. Cations are positively charged ions, anions are negatively charged ions. If you look to the far left on the periodic table, you'll find the alkali metals. When the alkali metals exist as ions, they are a +1 charge, and will include hydrogen in this group. The earth alkali metals are a +2 charge when they exist as ions. For the nonmetals, the nitrogen group is a -3, the oxygen group is a -2, the halogens are a -1, and the noble gases are a 0. And before each exam, I tell my students to write the common charges on their reference periodic table. Now let's try to understand why these charges are the way they are. To understand this, let's define the octet rule. The most stable configuration of an atom is one where the outer shell is full of electrons, thus achieving a noble gas configuration. For sodium, it is energetically favorable to lose one valence electron. When we remove the one valence electron, you'll see the remaining diagram is identical to the noble gas neon. Let's consider the example of chlorine. There are 7 valence electrons. In this case, you can imagine it would be easier for chlorine to simply accept one electron rather than lose 7. You'll notice in the 3p orbitals there is one unpaired electron. Chlorine will accept one electron and become the anion, chloride, and achieve the electron configuration of the noble gas argon.